Hi, I'm Inwoo Hwang from Seoul National University. Today I will introduce Text2PointCloud, text-driven stylization for Sparse PointCloud. Virtual spaces provide an immersive experience for metaverse, films, or games. With increasing demands for virtual environments, various applications seek practical methods to create realistic 3D assets with high-quality rendering results. Recently, some pioneering works have leveraged CLIP, the powerful joint embeddings of large-scale images and texts, and transform mesh or implicit geometries into stylized objects without requiring 3D datasets for training. For example, Text2Mesh is guided by the joint embeddings, and generates colors and deformations of the input mesh. Additionally, Dream Fields utilizes implicit neural representation similar to NeRF and generates three-dimensional objects guided by text description. However, the real-world 3D measurements are provided in a point cloud format, including multi-view stereo, LiDAR, and RGBD cameras. On the contrary, few practical frameworks allow editing the raw point cloud output to add geometric or textural details to the representation. While we can convert the point cloud measurements into other representations, it might destroy the complicated topology or suffer from noises or missing data. Our goal is to provide a text-based pipeline to directly stylize point clouds which can eventually visualize complicated topology with realistic colors. Given an uncolored point cloud and a simple text description, show raw points up to here, our approach stylizes the 3D point cloud such that it can be rendered into colorful objects with fine-grained details. Our pipeline iterates between stylization and upsampling. In brief, the stylization utilizes StyleNet, which deforms and adds colors to individual points. An upsampling module adds points respecting the current geometry. From now on, I will explain each module in more detail. One of the key modules in our pipeline is StyleNet. StyleNet is a neural network that generates the color and displacement of each point. Given the XYZ coordinates of the input points, we first apply positional encoding to capture high-frequency details. Then, each point passes through a shared network and then goes through separate branches that predict color and displacement. We assume that the input color is neutral gray and the displacement is initialized as 0. The output of the network adds an estimated color to the initial gray color. Also, the displacement vector shifts the current position. For each iteration, StyleNet is trained with the style loss and shape regularization loss. The style loss ensures we induce the desired style to the input point cloud. As we add colors and displacements for the points, we render the point cloud with a differentiable renderer to get multi-view images. The style loss encourages the images to be close to the input text in the joint embedding space of the image and text. When applying the style loss, we also augment images with random perspective transforms and random crops such that our stylization can generate details of various scales. Additionally, we apply shape regularization loss, which encourages the neighboring points to form a locally smooth surface. Our geometric changes intentionally allow independent displacements to visualize shapes with complex topology. However, the individual displacements and the subsequent stage of upsampling result in deviation from a clean manifold surface. The shape regularization loss enforces a coherent shape for the resulting geometry, and, therefore, a more realistic visualization of the stylized object. The shape regularization loss is composed of three terms. First, the uniform loss encourages the point cloud to be uniformly distributed and avoids irregular or sparse samples of points. Also, projection loss minimizes the deviation from the estimated local surface such that the points form a manifold-like distribution. The last term is the input loss, which maintains the deformed points close to the original input measurement. The next key module in our pipeline is non-learnable upsampling. We first sample uniform points from the current set of point using the farthest point sampling. For each sampled point, we find the k nearest points, and add the centers of the k nearest neighbors to the point cloud. Although this upsampling method may generate a spray of points with noise, the subsequent StyleNet effectively corrects the distribution by modifying the displacements of points with shape regularization loss and style loss. We iterate between our two main modules, StyleNet and upsampling process. Here, we briefly show the iterative process through animation. In every iteration, the upsampling process densifies point samples and the StyleNet gradually improves style by concurrently denoising possible random perturbations or upsampling artifacts. We show samples of stylization results of some objects using our method. The benefits of using the point cloud are prominent when we stylize objects to exhibit complicated topology. We compare our stylization result against Text2Mesh where the initial 3D model is in mesh representation. While the fixed connectivity of mesh inherently results in the predefined manifold structure, our representation is free to exhibit diverse topology of the surface details while maintaining locally smooth surfaces. We compare the visual quality of stylized objects against ablated versions. By comparing against the results without the iterative upsampling pipeline, we can deduce that our progressive upsampling module effectively creates dense points of the sparse input, which improves the visual quality. Also, without the shape regularization loss for StyleNet, the overall shape of the object is severely deteriorated as the points largely deviate from plausible geometry. In summary, we introduced Text2PointCloud, a framework to stylize and upsample the uncolored, sparse point cloud such that we can render high-quality 3D rendering of the given text description. While the point cloud can handle a wide variety of geometric details without connectivity constraints, it is challenging to maintain a geometrically plausible structure. Our pipeline iterates between gradually adding points and stylizing the object with the shape regularization loss. As a result, we can easily create dense samples of objects that express fine-grained ornaments with complex topology. Thank you for listening.